Hello everyone, today we are going to talk about chemistry. Everything is made out of atoms. When you look at the periodic table, you will notice that the periodic table has a bunch of elements. For example, carbon, hydrogen, copper, gold, etc. Those elements, the smallest units that they're made out of, we refer to them as atoms. And those atoms are made out of protons and neutrons and electrons that we are going to talk about in just a few. So this is the periodic table right here. So this is how it would look like. And we're going to talk about some of these different elements right here that are listed. And we're going to talk about what those numbers represent. But right here, you can see that there are so many different elements. So for example, this one is hydrogen. This one right here is helium, oxygen, nitrogen, carbon, etc. So we are actually going to talk about what the numbers represent. We're going to talk about what the symbols represent as well. And we are going to talk about how we can look at an element and figure out how many protons and neutrons and electrons it carries. We actually have elements within our body. We have about 25 elements within our body. There are four major ones. We call them the big four that we have within our body. And those major four are oxygen. So oxygen makes up about 65% of our body composition. Carbon makes about 19%. Hydrogen, about 10%, and nitrogen, 3%. So those are the big four: oxygen, carbon, hydrogen, and nitrogen. Now, other than those big four elements within our body, we also have some other ones: calcium, potassium, sulfur, sodium, chlorine. We also have, and all of these, by the way, the calcium, potassium, etc., we have about 4%, like they make up about 4% of your body composition. And then we have what we refer to as trace elements. And the reason why we call them trace, it's because we have less than 0.1% of those elements within our body. So we have a very little amount of those trace elements, but that doesn't mean that they are not important. So those trace elements are extremely important, even though we don't need that much of them. If we actually don't have the correct amount of those trace elements, or if we are totally missing those trace elements, that can cause so many disorders and illnesses. So those trace elements, they are very essential for life. One trace element that we don't need in huge amounts, but we do need it, is iodine. So iodine, even though it's a trace element, it is so important that we do get iodine, and we usually get iodine from the diet. Now, if someone does not get enough iodine from their diet, what happens is they can get the disorder known as goiter. So if you take a look at this image right here, you notice that this individual's thyroid gland, her thyroid gland is pretty swollen. So this is where you have the thyroid gland, and if it's swollen like this, we refer to that disorder as goiter. Now, one reason why someone might have goiter, so there are so many different reasons, but one reason is deficiency of iodine in your diet. So as I said, iodine is a trace element, but as you can see, if you don't have enough of it, it's going to cause that disorder known as goiter. Where can you get iodine? You can get iodine from dairy products, milk, cheese, etc. Eggs have iodine, iodized salt, So normally table salt doesn't have iodine in it, but they go ahead and they add iodine to it. And so whenever you see iodized salt, you know that they've added iodine. And this is kind of, iodized salt is the easy way to get your iodine. Again, if your diet doesn't have enough of the iodine, it's going to cause problems. Now, all of these elements like iodine, hydrogen, carbon, nitrogen, etc., all of these elements, as I said, they're made up of atoms, which is an atom is like the smallest unit of an element, and atoms, they're made up of those three particles: protons, neutrons, and electrons. So an atom would look something like this. In the middle, there would be the nucleus, and within the nucleus, you would have the protons and you would have the neutrons. And then surrounding the nucleus, we refer to them as the orbitals or the electron shells. This is where you would have the electrons circulating the nucleus in this fashion. So the thing about those particles right here, the protons, the neutrons, and the electrons, protons are positively charged, electrons are negatively charged, and neutrons, they're neutral. They do not carry a charge. So inside of the nucleus, you have the positive protons, and then you have the neutral neutrons. And then surrounding the nucleus, you have the negative electrons surrounding um, the nucleus of that atom. Now, when you look at the periodic table, if you're looking at a hydrogen element or if you're looking at a carbon element, you will notice that on the periodic table, those elements do not carry any charges, meaning you don't see hydrogen positive, you don't see carbon positive, you don't see hydrogen negative. And the reason why you don't see any charges, because the number of protons is equal to the number of electrons. And so their charges basically cancel out. So a hydrogen atom has one proton and one electron. So the positive charge of the proton is going to cancel out the negative charge of the electron. And so therefore, a hydrogen element is neutral. Carbon has 6 protons and 6 electrons. So again, those 6 positive charges are going to cancel out those 6 negative charges, leaving carbon to be neutral. And that's true for all of the elements on the periodic table. The rule is the number of protons, it's equal to the number of electrons. And so the positive charges will cancel out the negative charges, and therefore all of the elements are neutral. So when you look at the periodic table, you will notice a bunch of symbols, and each symbol has a number on the top and number on the bottom. First of all, the symbol is basically the elements symbol, and the symbol is trying to help you out, figure out which element we are talking about. So the letter O would mean that we are talking about the oxygen element. If you see H, that would mean it's the hydrogen element. C for carbon, S for sulfur, P for phosphorus, Cl for chlorine, etc. Now, so far, H for hydrogen, C for carbon, it's kind of making sense, but why is K potassium? I mean, the word potassium has no K in it. Why Na for sodium? Again, sodium has no Na. That's because Na and K, and actually all of those symbols, they are the symbols of the Latin word. So actually, so the whole periodic table is in Latin. Sodium, the reason why the symbol for sodium is Na, because sodium in Latin is natrium, and so therefore it's Na. Um, like, potassium, again, like the Latin word for potassium has K in it, and so therefore they went with the symbol K. Now, so this is the symbol right here. On top of it, you have a number, and that number is known as your atomic number. Now, what is the atomic number? The atomic number is basically how many protons does this element have? So how many protons is it carrying? And as we said, the number of protons are always equal to the number of electrons. So if oxygen, its atomic number is 8, that means that oxygen has 8 electrons and 8 protons, because again, the protons and electrons are always equal. Now, what is the number on the bottom? The number on the bottom, we refer to it as the atomic mass. And the atomic mass is basically the addition of the number of protons and the number of neutrons. So you would add how many protons you have and how many neutrons you have to get that atomic mass. So if you have 15.9, and you can just round, so let's say oxygen, its atomic mass is 16, and we know that 16 is the number of protons plus neutrons, and we know that oxygen has 8 protons. We can figure out the number of neutrons by just subtracting the two numbers. So one more time, the atomic mass, basically, it's the number of protons, okay? And you add that to the number of neutrons. Okay, and P is for protons. And we know that the atomic number is basically the number of protons. And we know that this is also equal to the number of electrons. So if I want to figure out how much or how many basically neutrons do I have, all I gotta do is I'm going to take my atomic mass, and I'm going to subtract my atomic number. So basically in this example it will be 16. That's for my atomic mass, which is again the number of protons plus neutrons, minus my 8, which is just the number of protons, and that would give me 8 neutrons. Now, in this example, oxygen has 8 protons, 8 electrons, and 8 neutrons. The number of neutrons doesn't have to be equal to the number of protons. So this example, yes, they are equal, but that's not going to be true for all of the other elements that we have. So one more time, atomic number is just the number of protons, and we know that it's equal to the number of electrons. Atomic mass, it's the addition of the number of protons and the number of neutrons. So anytime you want to figure out the number of neutrons, just subtract your atomic number from your atomic mass to figure out how many neutrons does it have. And as you can see, when you look at oxygen on the periodic table, you notice that it does not carry any charge. So you don't see oxygen positive, oxygen negative. And the reason why you don't see any charges, because oxygen has 8 protons and 8 electrons. So the charges are going to cancel out. So let's go ahead and kind of take a look at a few examples together. So let's say that, let's go ahead and take a look at, for example, sodium. Okay, so sodium right here. Notice how the number on the top right here for sodium, it's 11. So that means sodium has how many protons? It has 11 protons. How many electrons would it have? It would also have 11 electrons. Let's take a look at the number on the bottom. So the number on the bottom, 22.9. So you can go ahead and round. So the atomic mass for sodium, it's 23. If I want to figure out how many neutrons is sodium carrying, what are we going to do? We're going to take 23 minus 11, and that would give us 12. So sodium has 11 protons, 11 electrons, and 12 neutrons because I subtracted my atomic number from my atomic mass. Let's just take a look at another example. So carbon has an atomic number of 6. So what does that mean? It means that it has 6 protons. And right away, you know that it must have 6 electrons, since the protons are equal to electrons. Now, what's the atomic mass? The atomic mass is 12. What is the atomic mass? It's the number of protons plus the number of neutrons. So if I want to figure out the neutrons, I'm going to take my 12 minus 6. So carbon has 6 protons, 6 electrons, and also 6 neutrons. Okay, let's take a look at I. So I is the symbol for iodine. So iodine, as you can see, it has an atomic number of 53. So it has 53 protons, and it also has 53 electrons, since it's, again, protons and electrons are equal. And then if you look at its atomic mass, it's 126.9, so let's just round and say 127. So how many neutrons would it have? I'm going to make 127 minus 53, and that would give you 74 neutrons. So iodine has 53 protons, 53 electrons, and 74 neutrons. And that's how, again, you can calculate the number of neutrons, and you can figure out the number of protons and the number of electrons. Let's also talk about one more thing. Notice how the atomic number, like right here, so hydrogen, actually let's take a look at hydrogen together. So hydrogen has 1 up at the top, meaning that its atomic number is 1, meaning that it has 1 proton and therefore 1 electron. If you notice, its atomic mass is also 1. So what does that mean? How many neutrons does hydrogen have? Hydrogen actually has 0 neutrons because 1 minus 1 is 0. So hydrogen only has 1 proton and 1 electron and 0 neutrons. Now, we always say that the atomic number, that number up at the top, which tells you how many protons and how many electrons does the element have, this is what determines which element we are talking about. So for example, whenever they say, let's say you have an unknown element, and all you know about this unknown element is that its atomic number is 3. Then right away, you know that we are talking about lithium. Because if you take a look at this whole entire table, lithium is the only one with an atomic number of 3. If you go ahead and you know, you're given an unknown element, and they tell you that all you know about this unknown element is that its atomic number is 20. Then you know for sure we are talking about calcium, because if you look at this whole entire table, calcium is the only one with an atomic number of 20. So we always say that the atomic number is really what's going to help you figure out right away which element are you talking about. Now, you might say, well, why can't it be the atomic mass? Because check it out, right here, those two elements have the same atomic mass. And so therefore, some of the elements on the periodic table could have the same atomic mass, but none of them will have the same atomic number. And so if the atomic number changes, then your element changes. So if my atomic number is 3, it's lithium. If the atomic number changes and becomes 4, then it's not lithium anymore, it's beryllium. If it's 2, it's helium. And so therefore, the atomic number is really what determines which element we are talking about. Now, we have what's known as isotopes. Isotopes, it's basically, so when we talk about isotopes, that's when we are talking about atoms that have the same atomic number, but what's different about them is their atomic mass. So their atomic mass is different. So let's go ahead and kind of take a look at an example. So when we just looked at the periodic table, we talked about carbon, and like if you remember from the periodic table, we actually just had one carbon on that periodic table, just one C, and not multiple carbons, just one carbon on the periodic table. Which carbon is that? We refer to it as carbon 12. Now carbon, if you look at carbon on the periodic table, you would find the symbol C. There will be a 6 up at the top, and there's going to be a 12 on the bottom. Again, that 6 up at the top is the atomic number, so you know that carbon has 6 protons. We always say that the number of protons is equal to the number of electrons, so we also know that it has to have 6 electrons. Now, how can I figure out how many neutrons does this carbon carry? I am going to subtract 12 minus 6 because 12 is my atomic mass, and it's the number of protons plus neutrons. So I'm going to take 12 minus 6, and that would also give me 6 neutrons. Now, why do we usually call this carbon right here carbon 12? So we refer to it as carbon 12 because 12 is its atomic mass. So we refer to it as carbon 12. Now, it turns out that actually there's another carbon, and this carbon is known as carbon 13. And one more time, the reason why it's called carbon 13, it's because its atomic mass is 13. Now, notice something that's similar between carbon 12 and carbon 13. What's similar about them is the atomic number. The atomic number is the same, but what's different about them is their atomic mass. Their atomic mass is different. Carbon 12, its atomic mass is 12. Carbon 13, its atomic mass is 13. And so what's going to be different about them is basically the number of neutrons. So the number of neutrons, let me just highlight the number of neutrons right here. So the number of neutrons for carbon 12 is going to be 6, but the number of neutrons for carbon 13 is 7, because again, 13 minus 6 would give you 7. There's actually a third type of carbon, and it's known as carbon 14. And that's because its atomic mass is 14. So one more time, if you uh, subtract 6 out of 14, it would give you 8. So you would notice that those three different types of carbons, they all have 6 protons. So their atomic number doesn't change. And therefore, they are all carbons. Because if that atomic number changes, it's not going to be carbon anymore. So if that atomic number is now 5, or if that atomic number is now 7, we can't say that it's carbon anymore. It's going to actually turn into a different element. And so that's why isotopes, which are just different types of the same element, it's still going to be the carbon element, but because their atomic mass is different, their number of neutrons is going to be different. Usually, carbon 14 is actually a radioactive element, meaning that it has radioactive characteristics to it. And we actually use radioactive carbon 14 for carbon dating. If there is a fossil and you want to figure out how old is that bone, we figure out how many carbon 14 does it have within it. And carbon 14 has what we refer to as half-life. So after a certain amount of time, you lose half of the carbon 14 that you started off with. So I believe carbon 14's half-life is around 8,000 years. So every 8,000 years, you would lose half of the carbon 14. And so basically, they can take a bone and figure out how much carbon 14 is in the bone and figure out how many 8,000 years have passed. And so therefore, they can figure out how old is that bone. Now, why is carbon 12 the one that's written on the periodic table? It's because carbon 12 is the most common type of carbon we have in nature, and so therefore that's the one included on the periodic table. Carbon 12 is also the carbon that we have within our body. Actually, some of us could have carbon 14 within our, within your body. So some of us could have the radioactive carbon 14. It depends where you've lived, and it depends whether you've ever been exposed to like radioactivity in that area that you were in. So if anyone did get exposed to carbon 14, then they could actually have it inside of their body. And so one more time, different elements, we refer to them as isotopes. And what's different about them is their atomic mass, which means that what's different about them is how many neutrons each one has. And so, as I said, some of these isotopes could be radioactive. And then, as I said, radioactive atoms, they're actually not that stable. And so they break down spontaneously. So we always say that radioactive atoms have a half-life. So after a certain period of time, you lose half of it until you completely lose it all. So back to the thyroid gland. We kind of talked about the thyroid gland earlier when we were talking about how someone's diet could actually be deficient in iodine. They could start developing the disease or the disorder known as goiter. Now, another thing that could also affect the thyroid gland is ingesting radioactive iodine pills. So iodine also has isotopes, and one of the isotopes of iodine is actually radioactive. Now, they actually found out that ingesting radioactive iodine pills could actually destroy someone's thyroid gland. So why would someone take those radioactive iodine pills? In case someone has mass growing on their thyroid gland, or their thyroid gland is hyperactive and you want to slow it down, then the physician could go ahead and prescribe radioactive iodine pills that would be ingested, and those radioactive iodine pills would start breaking down the thyroid gland and kind of deactivating it. Now, once you ingest the radioactive iodine, it does have a half-life. Its half-life is around 8 days. So every 8 days, you would basically lose half of the iodine that you've ingested, half of that radioactive iodine that you've ingested. Of course, it depends what was your initial concentration of that iodine pill that you've ingested, how many 8 days it would take you for you to be completely free of that radioactive iodine. How would someone start losing that radioactive iodine once they've ingested it? It will come out through your sweat. It will come out when you void your urine. So basically it comes out with your body fluids. And so therefore we recommend that whoever takes that radioactive iodine pill doesn't get into contact with others because they will be excreting that radioactive iodine through their body fluids. Alrighty, let's take a look at this example together. Basically, this question is asking you, when you look at nitrogen, so N is the symbol for nitrogen, figure out how many protons and electrons and neutrons is nitrogen carrying. So for me to figure out how many protons and electrons it's carrying, I'm going to look at this number up at the top because that's my atomic number. So right away, I can tell that nitrogen has 7 protons and 7 electrons, which means I can eliminate answer 2 and 3. I want to figure out now how many neutrons does it have, so I'm going to look at that bottom number, which is my atomic mass, which is the number of protons plus neutrons. So since I know that it has 7 protons, I can go ahead and basically make 14. I'm going to take my atomic mass and I'm going to minus that 7, my atomic number, so 14 minus 7, which means that my nitrogen also has 7 neutrons. And so the answer must be number 4. So nitrogen has 7 protons, 7 neutrons, and 7 electrons. Now, as we know, each atom has protons, neutrons, and electrons. Now, depending upon how many electrons each atom is carrying, that's really what's going to determine whether an atom is going to bind with other atoms or whether it's going to stay on its own and it's not going to bind with any other atoms. To draw the electrons surrounding the nucleus of an element, we must follow 3 rules. The first rule says that first electron shell, you can fill it up with maximum 2 electrons. second shell and up, so second shell, third shell, fourth shell, etc., you can fill it up maximum with 8 electrons. And the third rule says that if you are going to draw several shells, you have to fill up the previous shells completely before you keep moving on to a new shell. So let's take an example. We want to draw the electrons that carbon is carrying. So the number that's going to be pretty important for us to draw those electrons would be the atomic number, because the atomic number tells you how many protons and how many electrons is carbon carrying. So the atomic number for carbon is 6. That means that carbon is carrying 6 electrons. So I'm going to go ahead and draw my first shell. So this is going to represent my first shell. And the rule says that the first shell, you can fill it up maximum with 2 electrons. So I'm going to go ahead and put down 2 electrons. Now I'm not done because I need to reach 6. So I'm going to have to draw a second shell, and I'm going to fill it up with 4 electrons. So my first shell is carrying 2 electrons, my second shell is carrying 4 electrons. If you add those electrons, you would get 2 plus 4, you would get all 6 electrons that carbon is carrying. Now, let's go ahead and take a look at this representation right here. Let's say someone drew it this way. They drew the first shell, and they only added 1 electron in the first shell. And then they went ahead and they drew a second shell, and they added in the second shell 5 electrons. So you have 5 electrons in the second shell with 1 electron in the first shell. If you add them up, they do give you 6. But why is that incorrect? Because the rule says you cannot draw another shell if that previous one is not completely filled up. And so that first shell, to be completely filled up, it needs 2, and you only drew 1. So this representation right here is incorrect because that first shell was not filled up completely. Let's take a look at another example. So let's say I want to go ahead and I want to draw the electrons that nitrogen is carrying. So nitrogen, its atomic number is 7. That means that nitrogen carries 7 electrons. So I'm going to go ahead and draw my first shell, and I can place a maximum of 2 in my first shell. I'm not done, I need to reach 7, so I'm going to have to draw a second shell, and now I am okay to draw a second shell since I've already completely filled up my first one. So after I completely fill up my first one, it's okay for me to draw a second one, and I'm going to go ahead and put 5 electrons in the second one. So that 2 plus 5 would give me 7. Now it's fine if your second shell is not completely filled up, because that's it, like you're out of electrons for nitrogen in this case. So first shell gets 2, second shell gets 5 for a total of 7. More examples. So let's say you want to go ahead and draw the electron shells of oxygen. So if this is the nucleus right here, what are we going to do? We're going to go ahead and draw the first shell, and the first shell can get a maximum of 2. First of all, when you look at oxygen on the periodic table, you will notice that oxygen has an atomic number of 8, which means you need to draw 8 electrons. So the first shell gets 2. I cannot add more than 2 for the first shell. And then I have to add a second shell. The second shell, I'm going to put down 6, so that when you add them up, 6 plus 2 would give you the 8 electrons that oxygen is carrying. Again, before you draw that second shell, make sure that the first shell is completely filled up. Hydrogen, if you look at the periodic table, hydrogen, its atomic number is 1. That means that hydrogen is only carrying 1 electron. So I'm just going to draw 1 electron shell, and I'm just going to add to it 1 electron. Notice how for hydrogen that first shell is not even filled up completely because it's only carrying 1. And as we said, the first shell is to be filled completely needs at least 2, but hydrogen, as you can see, is only carrying 1, so its first shell is not even completely filled up. Helium, if you look at the periodic table, helium has an atomic number of 2. So helium, I'm going to draw 1 shell with 2 electrons, and that would be, helium carrying 2 electrons in that first shell. Just a few more examples. Sodium, if you check it out on the periodic table, its atomic number is 11. What does that mean? It means that sodium is carrying 11 electrons. So I'm going to go ahead and draw my shells. So I'm going to draw my first shell. The first shell, maximum, gets 2. I'm not done yet, right? I need to reach 11, so I'm going to have to draw a second shell. The second shell, maximum, gets 8. You cannot add more than 8. Okay, so far, how many did I add? 2 plus 8 is 10. Am I done? Not quite. So I'm going to have to draw a third shell, and the third shell, I'm going to just add 1, so that 2 plus 8 plus 1 would give me my 11. Now, if someone drew it like this, they drew 2 in the first shell, 7 in the second shell, and then 2 in the last shell. If you add them up, it does give you 11. But why is that incorrect? It's incorrect because, as we said, you cannot move on and draw a new shell if the previous one is not completely filled up. So this one is completely filled up. That first shell is completely filled up with the 2 electrons, so it was fine to move on to the second one. But then notice how here for that second shell, you only added 7 electrons. Now, is that completely filled up? No, as we said, the second shell and up, for them to be completely filled up, they need 8. So that one right here would be an incorrect representation because your second shell was not completely filled up before you've moved on to the third one. Let's take a look at that other representation for drawing out sodium, and let's figure out the mistake. So right here, the mistake is at the very beginning. You did not fill up your first shell before moving on to your second and third shells. And as we said, the first shell, for it to be completely filled up, needs at least 2 electrons. So again, that's going to be the wrong representation if you drew it this way. Let's take a look at another example. Let's say I want to draw the electrons for potassium. So K is the symbol for potassium, and potassium has an atomic number of 19, meaning that potassium carries 19 electrons. So I'm going to go ahead, draw my first shell. First shell gets 2, cannot add more than 2. And before I move on to my second shell, I gotta make sure that my first shell is completely filled. So it is. So it's okay for me to move on to the second shell. Second shell can get a maximum of 8, no more than 8. So 2 plus 8 is 10. Not there yet. I need 19. So I'm going to go ahead and draw a third shell. Now again, make sure that before you draw that third shell, this second shell right here is completely filled up, which it is. So it's fine for me to draw that third shell. So how many am I going to add? Well, I'm going to add another 8. Again, before I move on, we'll check how many did we draw. So 2 plus 8 plus 8, that's 18 electrons. So I'm not there yet, so I'm going to have to draw a 4th shell, and I'm just going to add 1 so that I can have all 19 electrons. And again, make sure that each single shell is completely filled up. It's fine for that very last shell not to be filled up because, as you can see, we're out of electrons. Potassium only has 19, so even though that last shell is not filled up, I cannot add any more on that last shell. Now we're going to talk about whether your elements are stable or unstable. So for an element to be stable, the rule says that the last shell you draw, it needs to be completely filled up. And as you can see, some of the examples that we did draw together, their last shells were not completely filled up. And so that would mean that those elements are unstable. What does that mean? It means that you will not find unstable elements on their own in nature. You will find them bound to other elements. And the reason why they're going to be bound to other elements, because they are either going to share their electrons with other elements, or they're going to give up some of their electrons or gain some electrons for them to become stable. So let's just kind of, take a look at an example. So just a reminder, we said that the first shell gets a maximum of 2, and then the second shell and up, maximum of 8. Now hydrogen only has 1. So if you draw the shell for hydrogen, you're only going to draw 1 electron. So is hydrogen stable or unstable? Well, hydrogen only has 1 shell, so that's considered its first shell. And as we said, the rule says the first shell, for it to be completely filled up, needs 2. As you can see, hydrogen only has 1, so hydrogen is unstable. That means that hydrogen is not going to be found on its own in nature. You will always have it bound to another element. So hydrogen gas is actually H2 because it's unstable, and so you will have to have 2 hydrogens binding and helping each other out. They will share their electrons so that they can become stable. Because as you can see right now, it's unstable. And we're actually going to take a look at examples of how 2 hydrogens can actually help stabilize each other. We'll talk about it in a few. Let's take a look at helium. So helium, its atomic number is 2. So if you draw the shell for helium, I will draw 1 shell, and that 1 shell will get the 2 electrons. So that means helium is stable because, as you can see, its last shell, which is really its first one, it is completely filled up. As we said, the first shell is completely filled up with 2 electrons. So helium is definitely stable. And so helium is not going to feel the urge to bind to another element. You can find helium on its own because it is stable. What about carbon? Carbon has 6 electrons. So I'm going to draw 2 in the first one and then 4 in my last shell. Take a look at the last shell. The last shell only has 4. And as we said, second shell and up, you need at least, or you need a maximum of 8 for it to be completely filled up. So as you can see, carbon is not filled up, and so carbon is unstable. Again, why is it unstable? Because its last shell is not filled up. How many would carbon need for carbon to be stable? Well, carbon needs 4 more. Why 4 more? Because you're only looking at the last shell. So since carbon has 4 in its last shell, it needs 4 more so that it could become 8. Don't think of the total. Don't think of carbon is carrying 6 total electrons. So it needs just like 2 more to become 8 for it to be stable. No, always look at the last shell of the element, see how many electrons is it carrying, and figure out whether the shell is filled up or not. So since this is the second shell of carbon and it's only carrying 4, that's not completely filled up, so it actually needs 4 more so that it would be 8, and that would mean that it's completely filled up. What about hydrogen? If we actually go back to hydrogen, how many more would hydrogen need to become stable? Since hydrogen only has 1 shell, and that would be considered its last shell, it needs 1 more so that it would have 2 electrons. So hydrogen only needs 1 more electron so that its shell would be completely filled up with 2. And that's how we can figure out whether elements are stable or not. We look at their last shell and we see whether their last shell is completely filled up or not. If it is completely filled up, then we say that this element is stable. If the last shell of the element is not completely filled up, we know that this element is unstable, and that would mean that you are always going to find this element bound to another element, meaning you will never find carbon on its own in nature. It would always be bound to another element. It could be bound to another carbon, it could be bound to a hydrogen, an oxygen, a nitrogen. Same thing with hydrogen. You will never find hydrogen on its own in nature. You'll always find it attached to another element. Let's take a look at this example together. They're asking you how many electrons are in the outer shell of nitrogen. So they're basically asking the very last shell of nitrogen, how many electrons does it have? So the most important number that we are going to be looking at is the atomic number, because that's the number that's going to tell you how many electrons is nitrogen carrying. So the atomic number is 7. That means that it has 7 electrons. So I'm going to draw 2 in my first shell, and then I'm going to move on to my second shell, and I'm going to put down 5. So 2 plus 5 is 7. And so therefore, how many electrons are in the outer shell? Well, we have 5 electrons in the outer shell. Now, if we add another question actually, and I ask you for nitrogen, first of all, is nitrogen stable or unstable? So look at the last shell. The last shell only has 5. And as we said, second shell and up, for them to be considered completely full, they need 8. And so therefore, nitrogen is unstable. Now, another question, for nitrogen to be stable, how many more electrons would it need? One more time, look at the last shell. The last shell only has 5. For that last shell to be completely filled, you need to reach 8. So therefore, it actually needs 3 more for it to be stable. Because if you add 3 more to 5, 5 plus 3 is 8.